Kristen Atchison here, and we are going to do a hand calculation for an independent group's design t-statistic. So this is how I want you to do this. I would like you to pause the video, do these kinds of questions for this slide and the next, and then come back and look at the calculations. So again, practice is the only way that you're going to really get this well. Please pause the video on this slide or this slide. You can go back and forth between them and calculate the answers. Okay. For those of you who are still with me, who have paused the video and have done this and are looking to check your work, here we go. So first we're going to restate the null and the research hypothesis about the two populations. So our research hypothesis is that people who use mental imagery will remember more than those who did not. Again, we've got a directional hypothesis here. We know that because, if it'll let me go where I want to go, we know we have a directional hypothesis because if you look at this question here, it said, can psychologists conclude that mental imagery improves recall? So we know we have a directional hypothesis, so we have a directional test. So our hypothesis should indicate that. And if you look at the answers, again, that's what we have. We have a directional hypothesis. Those who use the imagery will remember more than those who did not. So we have mu1 is greater than mu2. For the null hypothesis, people who use mental imagery will not remember more than those who do not. So this is going to be the exact opposite. We have less than. Mu1 is less than mu2. The other thing you need to include here is this equal sign. If you just do less than, then you've left out 0. And so you don't have anything for what 0 equals. Remember, in a t-test, we're going to compare against this idea of no change of 0. So you have to make sure you're including that 0 in your mathematical expression of your null hypothesis. Okay, so we'll look at the characteristics of the comparison distribution. This is T-shaped because we're doing a t-test. It's a one-tailed test. Again, it's going to be a one-tailed test with because of that directional hypothesis, okay? That's how we know it's a one-tailed test. We have a directional hypothesis. And our degrees of, and our T, it's 18 based on the degrees of freedom from both groups. Our mean that we're comparing against is 0, which is again why we needed that null hypothesis to include that or equal to part, and that's because that mean is 0. Okay, so now we're going to go through the actual calculation part. We're going to calculate the sums of squared for each group. When we calculate the mean of 18, 19, 23, 29, 30, 31, 29, 26, 21, and 24. We get a sum of that of 250 and a mean of 25. What we'll do is we'll just subtract that mean from each. So 18 minus 25 is equal to -7. And we'll just do that all the way down. 19 minus 25 is equal to -6, -2, 4, 5, 6, 4, 1, -4, and -1. We're just going to square all of those values now. Remember, when you square something, you get rid of that negative or positive. You get rid of that sign, and we're just positive. So we'll square each of these values. And remember, this is the sum of squares, so we literally just add those values together and we get 200. We'll do the same thing for our second group. And when we add those values together, we get a sum of the x's of 190. And we get a mean of, oh, sorry about that. We get a mean of 19. So we'll do 24 minus 19 is equal to 5. We'll do the same thing here. 23 minus 19 is equal to 4. We'll go all the way down with those values. Okay, and we'll square each of those. So 5 squared is 25, 4 squared is 16, 3 squared is 9, 4, 0, 36, 4, 1, 16, and 49. Add those values together. The sum of the squares for the second group is 160. Okay, so now we're going to include that information and we're going to pool our variance. So we'll take our sums of squared 1, which was 200, plus our sums of squared for group 2, which was 160. We add that together, that equals 360. Our degrees of freedom for the first group was 9. Remember, we had 10 people in each group, so degrees of freedom for the first group is 9. Degrees of freedom for the second group is 9. That gives us 18. 360 divided by 18 is equal to 20. So our pooled variance is 20. We're going to take that value into this estimated standard error, and we're going to take, we'll take our pooled variance of 20 over how many people in each group? 10, right? So plus 20 divided by 10, okay, which is equal to the square root of 2 plus 2, which is equal to the square root of 4, which is equal to 2. So our estimated standard error is 2. Okay, so we're going to determine the cutoff. Again, we said it was a one-tailed test high, P.05 with that degrees of freedom 18 is equal to 1.734. Okay, so now we get to do our t-statistic. So the mean of group 1 minus the mean of group 2. We already calculated that, so we had 25 minus 19 minus the difference between the populations according to the null hypothesis. Remember, we said that was 0, right? So minus 0, and we're going to divide that by that estimated standard error that we just calculated. So when we do that, we get 6 divided by 2 is equal to 3. So our t value is 3 for this. Our cutoff was 1.3734. Our t value is in the cutoff. So if you look at that, we have 1.734. Our t value is 3, so it's in that shaded area. We're able to reject the null and support the research hypothesis that mental imagery did affect memory. So in APA style, the group that used mental images recalled more words than the group that did not recall mental images. And again, you see we have our APA style statement there. Notice we included both of the means so that you can see that difference in your APA style statistical statement. We have t, what kind of test it was, our degrees of freedom, what that t value was equal to, what we were able to reject the null at. And again, you're going to want to include that that's a one-tailed test because it is, again, a one-tailed test, and you need to let your audience know that. Okay, so we'll do an effect size. We were able to reject the null, so we have an effect, so we'll do a measure of effect size. If you do not reject the null, you do not do a measure of effect size. So we already have these values. So we know that, let me get that formula up, sorry. There we go. Mean of 1 minus mean of 2, 25 minus 19, divided by the square root of our pooled variance. We do that so that we get this estimated, standard deviation part alone, okay? So that's why we're doing that. So we get that, and we get that 4.47. So your formula may not have this piece on it. It may just say pooled standard deviation. So that's why we're doing that, is just to get that standard deviation by itself. So 25 minus 19 divided by 4.47 gives us 1.34. And that's going to be a large effect size, okay? So this was a large effect of memory. And again, you're going to include this value at the end of that statistical statement as well. Okay, so the test for homogeneity of variance, we need to, oh, I'm sorry about that. Let's see if I can go back. So for our Hartley's Fmax, now notice this Fmax is different than what we'll do later, an F-test for ANOVA. Okay, so this is completely different. This is something that we're doing. Homo means the same. So is the variance similar enough that we're able to do this test, right? Are these two populations similar enough that we can compare them? And again, a large value, a large difference between the sample variance, a small value near 1 equals similar sample variances. Okay, so what we're going to do to calculate this is we're going to just do the variance for each population. So we previously pooled that variance. We're going to just do them separately. This is my, if I had to tattoo a formula on my forehead, it would be this one right here, sum squared divided by degrees of freedom. This is the one we use again and again and again and again in this class. Sorry about that. I didn't actually calculate that for you. Again and again and again in this class. Okay, so the first thing we're going to do is, oh my goodness, I'm not having good luck today, guys. Okay, the first thing we're going to do is we know that we know we had a variance of 200, sums of square of 200. So we'll take that 200 divided by the degrees of freedom from each group. We had 10 people in each group, so that gives us degrees of freedom 9. So 200 divided by 9 is equal to 22.22. We'll do the same thing for the next group. We have sums of squared for 160 for this group, divided by 106. Oh my gosh, guys. 160 divided by degrees of freedom 9. Again, we know that it's 9 because we have 10 people in each group. 160 divided by 9 is equal to 17.78. Okay, so the way Fmax works is you have your two different variants for your two different group, and you really just put the largest value on top and the smallest value on bottom. So 22.22 is higher than 17.78, so it goes on top, and 17.78 goes on the bottom. When you calculate the difference between those, you get a value of 1.25. So our Fmax is equal to 1.25. And again, the closer the value is to 1, the more similar the sample values are. So that's how we calculate Fmax. Thanks.